Thanks, everyone. Welcome back. So today is part 2 of the final 3-part lecture series on statistical network analysis. Last time, we introduced several formulations of graph Laplacians. We talked about their properties in particular. We saw that the eigenvalues for the Laplacians corresponding to 0 tell us information about the number of connected components in the graph, and that the corresponding eigenvectors indicate component membership. Today, we're going to focus on the adjacency matrix. Again, we're going to see a very similar story. We're going to see the leading eigenvectors encoding information about the blocks and the clusters. One distinction here is that we're going to be talking about large in magnitude eigenvalues as the signal rather than the eigenvalues equal to 0. And we're going to be talking about stochastic mechanisms for generating graphs. All of the discussion last time was in the purely deterministic setting where we're given a graph, where we construct a graph in the absence of randomness and then study properties of the spectrum. Right? So in these notes, I wanted to start with the toy motivating example that you'll find in most textbooks, lecture series, et cetera, where we have what I'm calling A star as a stylized adjacency matrix, if you will. Now, this is not a binary sort of 0, 1 valued object, but what's important to realize is that, well, by this construction here, A star is blockwise constant. And if we look at an expansion of A star, what we find for this particular setting is that, well, sort of by inspection, it's rank 2, and we can write down its eigendecomposition very succinctly. Such that we identify its eigenvalues. U1 star, U2 star are the leading eigenvectors. And importantly, the second eigenvalue here indicates some separation or gap. There's no randomness at this point. We're just taking P and Q to be fixed constants here. But this denotes a gap, also a signal term, if you will. And in this setting, U1 star is just the vector of all 1s times 1 over root n to make this unit norm. And that's because we have constant row sums in this matrix, so the vector of all 1s is an eigenvector. And due to the block structure, we can write the second eigenvector as 1 over root n times the vector where the first n over 2 components are equal to 1, and the second n over 2 components are equal to -1. And so here, the sign distinction corresponds to the block structure that we have in this example. I should have mentioned here, just to be concrete, this is an n by n matrix, and the blocks here are size n over 2, okay? Very important here. But it's sort of hidden in the notation here with little n, okay? So this is a stylized setting. We're more often used to seeing an adjacency matrix A, whose elements are 0, 1 valued. And this is certainly the case if we're in the context of stochastic block models. Right? So remember, in lectures by Keith and Jesús, we've seen, for stochastic block model graphs, in the undirected case, the upper triangular elements, let's say, are independent random variables Bernoulli B tau I tau j, where B is a k by k symmetric matrix of connectivity probabilities. Okay, and tau here, this is our membership vector. So maybe we'll say a vector that takes elements in the set 1, 2. It's of dimension n. Tau I denotes the block membership of node I. Okay, and so now if we were to consider, as an example, B having the form PQ P with the specification that tau has n over 2, let's say 1s, followed n over 2 2s, then we get a situation where this A star corresponds to the expectation of our adjacency matrix, right? So we have then the ability to write A, if you will, equals A star plus E. Here, A star is the expectation of A, and E is just implicitly defined as A minus its expectation. Right? So we specify the model giving us this. We specify the data generating mechanism giving us A, and then the difference just gives us E here. Okay? So this concept of signal plus noise, if you will, is very general, very broad. It's by no means network-centric or restricted to networks. Has a very long, rich history in applied mathematics, in linear algebra. There are textbooks going back decades at this point. What's perhaps interesting is that in the last 10 or 15 years, there's been a lot of interest in revisiting this model and this simple concept. But when you have very specific structure for A star and E. In those cases, you can make very precise statements about situations that are not worst case. If we apply results from deterministic perturbation theory, those results by their nature capture all possible cases, good and bad, but in many statistical settings, we have a lot of structure that we can work with, and we're far removed from the worst case scenario. Right. Are there any questions or comments at this point? Okay, so we're going to call A star sort of our signal matrix, if you will. E is our noise or our error. And well, in this case, A star has very special structure, right? A star is actually rank 2, despite being an n by n matrix, right? Large matrix, but rank 2. It's a dilation of the 2 by 2 B matrix that we have here. And so a big question then to ask is, can we infer properties of A star using only knowledge of A? So think of A as our data. A is our observable random matrix, we don't get to observe A star. But for example, if we could say that the second leading eigenvector of A is close in a suitable sense to the second leading eigenvector of A star, well, then we observe that that eigenvector denotes information about the community structure, right, as we saw with the Laplacian. I mean, in this very special case, whether you work with this adjacency or the symmetric Laplacian, the story is basically unchanged. It's a very homogeneous setting, but it's still nice to look at it in this way. It's still, I think, clear from an adjacency point of view. So can we infer properties of knowledge of A for the case when we have low rank or approximately low rank structure A star? Let's write its spectral decomposition in this way. Low rank A star. Well, A need not be low rank, and usually it's full rank with probability 1. But we can still, in many situations, decompose it, provided there's a sufficiently large gap, if you will, between the eigenvalues. So we have here, this is the, let's say, the top rank D part, and this is the residual, or what remains after the bulk. And so the big question then would be, in our discussion here, to what extent are the leading eigenvalues in A, so I'm written here as this diagonal matrix, to what extent are they approximately those of lambda star in the population? And another question is, to what extent is the matrix of leading eigenvectors of A close to or approximately the matrix of leading eigenvectors of A star? Right. In the language of perturbation theory, we observe A as a perturbation of A star by E, and we ask how close are the perturbed or sample eigenvalues and eigenvectors to the original unperturbed model. Right. Okay. Any questions, comments at this point? No? Okay. All right. So we're going to proceed to investigate both of these questions. First, we're going to start by thinking about the eigenvalues. And so we have a very, at this point, well-known and well-utilized theorem due to Weil, which says the following. If you have exactly this setup here, a symmetric signal plus noise matrix model, then let's write the eigenvalues of A star by lambda 1 star all the way to lambda n star. Similarly, lambda 1 to lambda n for A. Then for all indices 1 through n, the difference between the sample and the population eigenvalue is bounded above by the operator norm of E, the noise matrix. Okay? This is a purely, this is a very general setting, right? General deterministic means it handles both best case and worst case, right? In particular, what this says is that for small noise level measured through the operator norm, it has a very small effect uniformly on the spectrum, right? That means uniformly over all I, right? So in particular, the max over all I is bounded above in operator norm, right? So this is a very, very strong statement, okay? And so for us, we're going to be interested in settings where the noise has some stochastic structure so that it concentrates with high probability. And then for such an event, and given a bound on E in operator norm, let's say, then provided lambda star exceeds some quantity that's larger in magnitude than the noise level, then we'll be able to apply this usefully in settings of this form, where we have stochastic noise modeling the signal. Right? And we'll be able to make perturbation statements on good events that hold with high probability. Okay? Any questions about this theorem? Okay. I mean, certainly there are a variety of perturbation results for eigenvalues and eigenvectors. For these notes, I'm really just streamlining the presentation and the discussion. I mean, certainly there are others that we could use. Cauchy interlacing of eigenvalues is useful in some contexts, but here this is going to be sufficient for our discussion. Okay. All right. Now to talk about the eigenvectors, we need to think about what is a good or appropriate choice of distance metric, right? To talk about closeness of eigenvectors, or if you will, really matrices of orthonormal columns who then give us bases for low-dimensional subspaces in our ambient space. Right? So let's let capital O math font n pi d denote the set of all n by d matrices with orthonormal columns. Okay, so for our setting, you can think of each column of this matrix, of a matrix in this set, is an eigenvector. In this case, because our eigenvectors for symmetric matrices are orthonormal, right? We can find such vectors. Okay, so for any two such matrices, we have two notions of subspace distance that we can define, one using the operator norm and one using the Frobenius norm. Okay, and so this distance is saying take the two matrices that are your input and try to align them up to orthogonal transformation in both operator and Frobenius norm. Okay. Now visually, we've talked in this lecture series about embeddings and low-dimensional representations, right? So what's really going on here is the matrix U has rows who are my fingertips. The matrix U star has rows who are my fingertips here, and this matrix R is reorienting this configuration without actually changing the relationship between the rows, right? I'm simply changing my perspective or rotating my wrist and trying to say that these point clouds are close in a certain sense. Here, that sense is operator norm and Frobenius norm, okay? Now, it's perhaps a little bit unclear at first glance, whether we can solve, this problem. Can we find an R explicitly that solves either of these optimization problems? How do we sort of evaluate this quantity? One nice aspect or fact is that these formulations of distance metrics are equivalent to looking at distances of the orthogonal projection matrices corresponding to these inputs. And equivalent in the sense that each of these distances can be upper bounded and lower bounded by differences of orthogonal projections, again, here in the operator norm for this row, in the Frobenius norm this row, and the constants here are universal. I mean, the universality of the constants here is important. We know that in general, if you're working with finite dimensional vector spaces, all norms are equivalent, right, in the sense that we can upper and lower bound them by another norm, but where that constant may depend on the ambient dimension that you're in. Here, this holds regardless of the dimension that we're considering, okay? This is also a nice representation because we know that orthogonal projections onto low-dimensional subspaces are unique representations for those subspaces, right? Simply having a collection of orthonormal vectors that span their space is not a unique representation, right? I could flip the sign on one of the columns. That doesn't change the span of my space, all right? But it does change the matrix. Nevertheless, that choice of sign flip is accounted for in this interpretation of rotation, right? Rotations and reflections. Okay. Any questions about these distance metrics? Okay. Well, going back to the previous version, we said that they are equivalent, but there's also, if you want to think about it a little bit more, an exercise that you can show, which is at least in the case of the Frobenius norm here, if you take these input matrices U and U star, if you form the D by D matrix that is U star transpose U, you take its SVD, and you keep the left and the right orthogonal matrices and define this product matrix, which is itself orthogonal, then you can show that this rotation actually achieves this Frobenius norm minimization problem. Right? This is convenient for a variety of reasons. I mean, one, sort of practically, is that if you're running a simulation and you're working with this choice of distance measure, you can actually numerically compute this example. But actually, this matrix, which is also referred to as the orthogonal matrix in the orthogonal Procrustes problem, this actually appears in many of the proofs and the perturbation analysis. So you can actually use this matrix here and this fact to prove the equivalent statement we had on the previous page, using the idea of canonical angles and distances between principal subspaces, which includes concepts like the CS decomposition, the cosine sine decomposition. Right. Great. Any questions, comments? How about this? How about at least one question about any of this so far?
Okay, one question is,
please.
What happens with the operator?
Great question. So in general, for other norms, there is no clear way to solve this problem explicitly. I've seen some recent work on Riemannian optimization that looks at this problem. But once you move away from the Frobenius norm, there's no hope in general, as far as research that's been done for a few decades now shows, to actually say anything. What's nice, though, is we can sort of often translate statements about the minimization in operator norm to a statement about this Frobenius norm if you're willing to upper bound that minimization by this specific choice. Yeah, but that's an excellent question. Right. Actually, later in the lecture, we'll look at these distance, this difference of orthogonal, this difference of orthonormal matrices. I'm using even a different norm, and there we're again going to be interested in this minimization, but we can't hope to actually analyze it directly. So the analysis under the hood makes use of this orthogonal matrix. Yeah, it's a great question. Okay. So now that we've talked about appropriate notions of distance between subspaces, we can present a theorem which highlights the relationship now between signal and noise in this perturbation setup. So again, we have the signal plus noise setting symmetric matrices. We have a general deterministic perturbation theorem due originally to Davis-Kahan in the 1970s, but substantially sort of revisited and reformulated over the years, saying in this version of it, provided the noise level as measured by your operator norm of E is not larger than a constant times the eigengap in your population. Right, so here we're now saying that this matrix A star has a gap between the rth and r plus first eigenvalue. If it's low rank and rank r, then we can set this equal to 0. But more generally, if it has rank r plus 1 or greater, then the operator norm and the distance metric and the Frobenius norm distance metric have bounds that look like an inverse signal-to-noise ratio. In the numerator, we see dependence on E, right, our noise, again an operator norm. And in the denominator, we see the spectral gap appearing. And what this is saying is that if the spectral gap is large enough as a way of quantifying signal compared to the noise level, then these subspaces will be close. This is for convenience for ordering. That's right. I mean, in general, you could have positive and negative eigenvalues, and there are perturbation results that look at, different gaps, whether you're looking at the gap on the positive side and the gap on the negative side. But this is, I think, the simplest way to present it, even if it's not fully general. Right? Great. Okay, so Weil's inequality for eigenvalues, the Davis-Gahan theorem for singular subspaces, these are going to be our key tools for looking at what we're going to call L2 perturbation theory. So that means perturbation in an overall L2 norm sense, which we're then subsequently going to refine through the discussion of entry-wise perturbation theory and entry-wise eigenvector estimation. Okay. So now what we're going to do is present a few examples of concentration inequalities for E and operator norm, so that we can say, ultimately with high probability, E and operator norm is not too large. Therefore, if these lambda stars are sufficiently large, then with high probability on that event, we'll be able to leverage these results. Right? So in these notes, I've provided a few different examples of existing operator norm bounds. This is one taken from Roman Vershinin's high-dimensional probability textbook. Forgetting about networks or graphs for the moment, we can think more generally about what are called sub-Gaussian random variables, which I think Keith mentioned at least briefly in the first week. And the idea is that we have E is a symmetric matrix of noise, okay? But now, in addition to allowing this Bernoulli, the centered Bernoulli structure, we could allow a Gaussian random variables, we could allow other bounded random variables, or in general, random variables whose tails decay at least as fast as Gaussians. Right? Okay, so let E be one such matrix, then there exists a universal constant C, so that for any choice t greater than 0, the probability that E exceeds this threshold is small for given your choice of t. Is bounded above by 4 times exponential negative t squared. Right? So take t to be, for example, log n, if you will, or square root log n. Here, this matrix is again n by n. We see in this upper bound a term square root n plus t, okay, showing that regardless of our choice of t, we're not going to do better than order square root n. We see here some dependence on the underlying random variables. Here, this is the maximum over the Orlick 2 norm, or the sub-Gaussian norm on the random variables Eij. Okay. For centered Gaussians, this is of the order the standard deviation of random variable. For centered Bernoullis, this is order a constant. So we should think of, in this setting, this quantity being stable, or perhaps not growing quickly in n, in which case we have this bound on E and operator norm exceeding some threshold. Okay? All right, let's look at another operator norm. Easy to use off the shelf. This one is in the reference Chen et al. Spectral Methods in Data Science, leveraging and building on the paper by Bandiera and von Handel in Annals of Probability in 2016, which characterizes the expected operator norm for symmetric random matrices with Gaussian entries. Okay. So again, E is a symmetric random matrix, independent entries on and above the diagonal, centered, so mean 0. Here, we're assuming that they are bounded by some uniform quantity b, and we're going to assume that all of their variances are uniformly upper bounded by sigma squared. Okay? Then what we have is, again, a high probability concentration inequality. Stated slightly differently, though, we're saying for any user-specified choice of constant little c, there exists another constant, capital C, allowed to depend on little c, such that the probability E in operator norm exceeds some threshold is small. And here, small is captured in the form n to the minus c. Okay? In the previous slide, we saw exponential of negative t squared. Right? If we had plugged in a constant times square root log n, we would have been able to massage that equation to look like this form here, n to the minus c. And the idea is that in applications in many settings, it's sufficient for us to work with events that have probability at least, say, 1 minus n to the negative 10, right? Or some large but fixed constant c, rather than keep the exponential form. Okay? This approach allows us to apply Borel-Cantelli, and in other settings is sufficient for our purposes. Maybe it's worth just, I guess, noting that for, if x is a normal mean mu and variance sigma squared matrix, just random variable, excuse me, not matrix, then the probability that x deviates from its mean by more than c sigma log n, this is bounded above by 2 n to the minus c, where we can specify our choice of c, say 2, 4, and then capital C here introduces it. And in this case, this is actually just square root of 2 little c. Right? So for any positive c that you give me, that in turn defines a threshold so that with high probability we do not exceed that threshold. Okay, and we see a similar story from the previous slide, namely that there's again a root n factor here multiplied by sigma, and we have another term cb square root log n, and this is capturing the concentration properties of E in operator norm. Okay, I mentioned on the previous slide that the Orlick 2 norm for Gaussians looks like the standard deviation, and so we see sort of that resemblance here compared to the previous slide. Okay, how about one more concentration inequality, this time tailored to our setting of random graphs, and in particular stochastic block models and others. So now let's let A be our symmetric adjacency matrix, generated independent Bernoulli. Here I'm using P to denote the matrix of probabilities, right? Assuming that n times the max of your probabilities is less than or equal to d, for d at least some constant times log n. Then we have a statement saying that, well, for any user-specified choice, little c, there exists a constant capital C, so that, well, the difference of A minus P, which is simply, in our previous language, E, in operator norm, the probability that this exceeds a quantity order square root d is no more than n to the minus c. Okay? So now here, we have to take a moment and realize that the assumptions here do place restrictions on the networks that we have, right? Namely, this result holds for semi-sparse but not too sparse graphs, right? We're saying that D has to be at least C0 log n, and D is an upper bound on n max ij p, right? So this would fail to hold if the probabilities were allowed to depend on n and if they were going to 0 too quickly. Right? So again, this result holds, but only for, let's say, semi-sparse graphs and not in the fully sparse case. I mean, in fact, it's provably the case that we don't get this concentration in the sparse case, where probabilities look like order 1 over n. Right? Spectral concentration breaks. We can't apply the traditional perturbation theory that we're talking about here. And the reason is that we're going to get some unusually high degree nodes in the adjacency matrix, and that's going to corrupt our perturbation statements. The noise and the signal start to become more difficult to distinguish for very sparse graphs. So these perturbation theory techniques won't work beyond a certain threshold. That's why for most existing spectral results that don't do some additional normalization or preprocessing, you'll see log n appear as a requirement for expected degree and stuff like this. Now this result can be generalized a little bit, so we can remove or we can modify this statement to look at maximum row sums of P just to allow for a little more heterogeneity. This is mentioned in the reference. By the way, this is a theorem from a paper by Lane Rinaldo in Annals of Stat 2015 that establishes consistency of spectral clustering for stochastic block models. So this is one of the I would say this is one of the papers to look at if you're interested in stochastic block models and spectral methods. One of the earliest and most influential, certainly. All right. Okay, so let's take all these ideas and apply them now. And I've stated this in the form of an exercise, but we can just sort of walk through the statement at least, and the proof sketch follows just directly from everything we've been saying so far. But let's now see how, in an L2 sense, we can obtain useful perturbation results. So we're in the setting that we started with, right? A is our random adjacency matrix, right? We're not going to assume anything about block structure here. Now, we talked about how when there is block structure, then it's very clear why we might want to do this. But in general, we can think about this perturbation story. Right? So the probabilities Pij are going to be between 0 and 1. We're going to introduce this additional scaling factor rho n. Right? This is going to allow for some sparsity in the model, not too much, but some. So we're going to allow rho n to possibly go to 0 if we want, or just a fixed at a constant. We are going to assume, though, that P has rank R. Right? And here, let's think of R as fixed for simplicity, but in general, R for many of these results is allowed to grow with n, the number of nodes in our graph, or the size of our matrix. So we have a few claims then. The first is that if n times rho n is at least log n with some suitable constant, then the operator norm of the difference of A minus P is bounded above with high probability of the order square root n rho n. Okay, and this result boils down essentially to an application of the previous theorem that we saw for random graphs, right? An operator norm A minus P. So if your network is not too sparse, then this difference, or the noise matrix, if you will, concentrates. So it looks like square root n rho n. Right? If we think about the entries of this matrix here, right, this is our parameter matrix, if you will, that governs the Bernoullis, right? And if the probabilities of success or an edge are rho times some constant, well, then the variance is going to be rho times some constant times 1 minus rho times Pij. And if we take the square root of that, that looks like order root rho n. So that's sort of indicating that this is perhaps what we might expect here. The second bullet point now says that if n rho n continues to be at least order log n, and provided the rth eigenvalue of p in modulus is at least order n rho n, is at least of this order of this threshold, then we have a bound on the operator norm distance between the subspaces that looks like order square root n rho n over lambda r star. Right? Now, this is just a direct application of our previous Davis-Gahan theorem and our operator norm bound that we have here. Notice that this bound holds with high probability. It holds on the good event that we can bound the noise in operator norm, right? Because at that point, then the signal strength is sufficiently large, as quantified here through lambda r star. Okay? We can also make a statement about the rank R approximation to P, right? P is rank R by hypothesis. Here, U lambda U transpose is the low rank approximation of A in this notation that we have here. And this is bounded in Frobenius norm with high probability of the form constant square root R square root n rho n. Right? I mean, we could have bounded the operator norm here too, but since this is a low rank matrix, right, the Frobenius norm and operator norm are going to be related to each other by a factor depending on that rank little r here. Okay, and so this is nice because if we were to look at a relative measure of Frobenius norm, say, this divided by P in Frobenius norm, then we would have a quantity, a relative error quantity that would be going to 0 with high probability for large networks. Let's pause for a moment and see if there are any questions about this slide. That's right. Essentially, it's their operator norm bound plus a version of the Davis-Gahan theorem gives consistency for SBMs. There's also a degree-corrected variant in there with some normalization. The connection, though, is, so I mean, we might ask, how do we leverage these results now for consistency? I haven't actually defined sort of an error metric for clustering or anything like this. But in Ley and Rinaldo, what they look at is 1 plus epsilon approximate k-means clustering. Okay, so this problem can be formulated as a Frobenius norm minimization problem, right? One that is computable in polynomial time, right, in contrast to sort of the general k-means problem. And they relate the performance of k-means clustering directly to quantities that appear in the Davis-Gahan subspace perturbation theorem. So what that means is if you can control the perturbation theory, then that directly implies a statistical guarantee for clustering. Yeah, great question. All right, so let's return to this stylized model we saw a moment ago and think about what a result for this model in the L2 norm sense might look like. Now, for convenience, we're actually going to transform the model here, which is rank 2, into just being rank 1. That simplifies the perturbation analysis, and ultimately, by redefining these quantities, we're going to end up with just this eigenvalue and just the signal eigenvector here. Simplifies analysis. Now, to do that, we are using knowledge of the population parameters, if you will, in the model, but this is sort of a stylized example, so it's really just an illustration, right? Let's consider our, let's say, toy 2-block SBM model. Let's maybe just recall so now rewriting the model is going to give us that we're going to have just a rank 1 spike. So now lambda star is just this eigenvalue, and the corresponding eigenvector is now the one that denotes cluster separation on the basis of sign. Right, and so our procedure now is going to be twofold. To compute leading eigenvector of, I'm going to call it A prime because it's not the same A that we had before. But to spare us a little bit of time and notation, I'm not going to write all of those details here. But compute the leading eigenvector of A prime. And since we're interested in clustering, well, let's actually define clusters using the notation as follows. So compute what we'll call our cluster estimates. And let's use this notation that xi is just the sign of ui. And so this is just going to be, in our case, plus or minus 1. Depending on whether the ith component of our sample eigenvector exceeds 0 or not. Right, and so in this setup, we can define a loss function. So we can ask about what is the loss when the true vector of memberships is given by xvec star, and when x is the one that we compute from our data. And let's write it in the following way. Min so this is going to be 1 over n times the minimum sum over all our data, and we're just counting the number of disagreements. Up to choice of a sign flip. So let's say alpha xi star here. Okay. Is it clear? We have two membership vectors, if you will. We're trying to compare them. They each take one of two values, and we're just trying to determine up to a global relabeling of those values how many disagreements there are. And we're going to call it our loss function here. All right, so we have a theorem. Really, it's a sketch of a statement or an informal theorem, which is, in this setting, suppose further that p is not too small, in particular that p is not smaller than order log n over n. And that square root of p divided by n is little o of this gap, of this difference between p and q. Then with probability at least, let's say, something like 1 minus big O n to the minus 8. So this is where the previous form that I introduced comes into play. So we've chosen some suitably large constant here, n, 8, and maybe we allow some large constant in front. But then with this high probability, we have that this measure of L2 normalized loss is going to 0. And these are all statements as n is growing, right? Right? Right. And so the way that we could prove this is to relate this loss statement to a statement about how close our sample eigenvector is to the true population eigenvector here in L2 norm, right? And then to show that this L2 difference appears suitably normalized, and we get a quantity that tends to 0 as our graph grows. For graphs that are not too sparse and for which there's enough separation or distinction between the two distributions, right? Here P and Q parameterize the different Bernoulli distributions. So the problem becomes harder if those values become smaller. Right? So what this is saying in words is that for large graphs with high probability, the ratio of misclustered nodes is going to 0, right, with high probability. That doesn't guarantee that every individual node gets perfectly clustered with high probability in the large graph limit. Maybe there are log n vertices that get misclustered in some regime, but log n over n is still going to 0. This is all that L2 perturbation theory can tell us for the moment. Okay. Excellent. But now, going back to our original problem, it would sure be great if we could make an even stronger statement about this perturbation theory. Namely, if we could show that entry-wise, the leading eigenvector of the data is approximately this eigenvector. Because if we could do that, then we would be able to say, perhaps, that uniformly over all nodes in your graph, we can perfectly recover the community memberships. And that's exactly the motivation and inspiration for L infinity and L2 to infinity vector and perturbation theory. Great. All right. So in the rest of today's lecture, we're going to highlight the ingredients and use of entry-wise and row-wise perturbation analysis. Okay. And in this setting, I think it's really helpful and instructive to go back to our earlier discussion about distances between subspaces, which we're thinking of as collections of eigenvectors for some underlying matrices, and really to think about this fingertips analogy, right? Now what we want to say, moving forward, is that uniformly, sort of in the large n limit, with probability tending to 1, all of my fingertips are getting uniformly closer to fingertips on my other hand. Right? That's really what's going on here. first, let's introduce a new concept for norms and distance, which is the following. So A is a matrix, the 2, infinity norm is what's called a mixed subordinate operator norm on matrices, defined in this way. It's mixed because we're taking a soup over the L2 unit ball, and then we're looking at AX in L infinity norm. Okay, maybe I'll just make a note here. Recall that the operator norm, can actually be written or thought of equivalently as the 2, 2 norm. We call this an operator norm in the first place, but this is nothing more than this same setting, but with L2 and L2 vector norms here. But now we've switched one of the vector norms. Okay. Has anyone seen this norm before? Maybe in some places you see a notation like 2 arrow infinity. Has anyone seen this norm before? Okay, good. Okay, so people are listening, are engaged. Great. Did he define it? Allude to it? Yeah? Does anyone remember what he said? Yeah, so I mean, it's not quite clear what's going on here, but I do claim that this is the same as if we were to take, well, let's write it in this way, max over I this is the same as if we were to take the max L2 row norm of A. Okay? I mean, not clear from this formulation, but I mean, he did prove it. No, yeah. I mean, it's an exercise, if you will, right? Okay, so why is this norm useful? Well, if we have quantities of the form u minus u star r in 2 to infinity, then this is exactly saying that my fingertips get uniformly close to each other modulo this orthogonal transformation r when this quantity is small. This is a uniform measure of closeness between the rows of these matrices. Right? And perhaps interestingly, this is preserving some of the underlying geometry, because if we were to multiply A on the right by an orthogonal matrix, well, that's not changing the row norms, right? And in particular, this norm is invariant to such rotations. Not so if we were to multiply it on the left. For the operator norm, Frobenius norm, we know both of these are unitarily invariant norms, right? They don't care about orthogonal multiplication on the left and the right. But here we have a sort of a partial rotational invariance. So let's see. So this is uniform control over row differences. And hence, if we want to think about embeddings, right, this is saying the point cloud we compute from our observable data is in some sense close to this matrix here. Now, maybe this inclusion of R is causing some concern or sort of unpleasant, or we might ask, do we really need it? The answer is yes, we do in principle, because, right, eigenvectors are only defined up to a sign flip, and if we have repeated eigenvectors, repeated eigenvalues, then we could apply a rotation to our collection of leading eigenvectors and still have a collection of eigenvectors for those eigenvalues. So yes, in general, we do need R, but what's nice is that it doesn't change the properties of the point cloud, right? If you were to apply k-means clustering to a point cloud like this or like this, well, I haven't changed any of the inner point distances. So in principle, your results should be unaffected up to perhaps some numerical strangeness. Okay? So this norm will be our choice of interest, particularly in the general case when we have rank R matrices. In the one-dimensional case, this just boils down to the L infinity vector norm, right? So we have L infinity and L 2 to infinity perturbation analysis. That's what we're getting ready for here. Questions, comments? Is it convincing that this might be a useful notion of length or distance or something, a norm? Yeah. All right. Okay, so here is a quick sketch. Now, actually, before we do that, okay, let me hide this again. Let's do the following. Let's think just about an orthonormal matrix U, tall and skinny, right? Tall because, say, we have many nodes in our network, skinny because we only have a few eigenvectors that we're interested in. What can this look like? In any sense that you define. All I tell you is, okay, and this. I give you this matrix. What can you tell me about this quantity? U is a matrix of orthonormal columns, and I'm asking you, what can you say about the 2 to infinity norm?
Well, it's less than 1 or 2 or something. Less than square root of t. Because in each row we're going to have entries bounded by 1 absolute value.
That's right. Yeah.
Probably very weak.
Okay, so basically, yeah, so we're using the fact that this is the maximum Euclidean row norm. It sounds like you're bounding it above by an L1 norm, and since there are D elements, each of which is bounded above by, oh no, I'm sorry. Yes, okay, you're just looking at bounding the entries above by 1 taking the root. Right, okay, so we have this. Okay, so fine. Can we do better? Okay, we have a candidate of 1.
We have a lower bound maybe of square root of d over n or something like that. It's just from.
Okay, let me rewrite. Any other suggestions? Any votes for one or the other?
Yeah, the lower bound you can get from something like, can be achieved by something like a Hadamard matrix.
Okay, yep.
Or a few columns of Hadamard.
Okay.
And you get so the general lower bound just by taking something like, well, you add up the L2 norm squared of all the rows, and then you divide by n.
Yep. Okay. So it sounds like at least one person is happy with this. Some people are nodding. Okay. What about an upper bound? So indeed, that is true, right? So I'm going to write it a little more nicely here. So in general, we do have this lower bound. That would have been upper bound. Well, so here we're not, I said this is tall and skinny. For, conceptually, maybe that's useful to think about, but an orthogonal matrix would still be a matrix of orthonormal columns, and in that case, all the L2 norms for the rows are 1. Right? So I claim that actually here we can show this is less or equal to 1. That's right. So this is kind of a little exercise, if you will. Why is this useful? Why is this nice? Well, let's go back to this example here. Right? We have a vector that is, if you will, maximally delocalized. Right? All the entries are absolute value 1 over root n. So that's giving us the lower bound regime. So here, what we have are delocalized vectors versus localized vectors. Right? So think the vector 1 over root n versus just a standard basis vector. Right? This is a standard basis vector, a collection of standard basis vectors. We're just reaching the maximum here. Right? Okay. So one of the punchlines in L infinity and 2 to infinity perturbation theory is that the structure of the eigenvectors, here, if I want to be really careful, I'm talking about U star. These vectors, depending on whether they're localized or not localized, either do or do not disperse the influence of the noise matrix on the overall perturbation in A. So it's going to be the case that this is what we want in order to obtain L infinity and L2 to infinity very refined entry-wise perturbation arguments. In settings where we don't have sufficient delocalization, settings such as this, then we can't improve upon traditional L2 analysis. Right? And so I really want to emphasize here that if we think sort of entry-wise about trying to recover this matrix, then we would like to say that maybe all the entries of our sample eigenvalue that we compute look like roughly order 1 over root n, and that we can control that uniformly for all nodes in the graph, for all embedding vectors.
Yeah, so I guess we have one mini course about sparsity, and this is about the opposite of sparsity, but that makes no sense.
Oh, I see. Okay, yes. So like, I would say yes and no. The reason is that, so for this stochastic block model example, we have this, right? So this is not sparse in the sense that the entries are not 0, right? However, SBMs are themselves sparse latent factor models, if you will, because we can write them as ZB, Z transpose, where here Z is a sparse membership matrix, right? It's a great comment though. There's been some really interesting work recently. I'll advertise Carl Rowe, who's also at Wisconsin, showing that Varimax factor rotations combined with eigen decomposition truncation can be used in a meaningful way to relate properties of the eigenvectors to these sparse latent factor matrices for estimation. So my discussion right now is not doing them justice, but I would encourage you, if you're interested in sparsity in this sense and in graphs, then that would be a paper to look at. It was a JRSSB discussion paper published a few years ago. So, great. Maybe one more thing is that I'll mention back to the Lane-Rinaldo paper for 1 plus epsilon approximate k-means clustering. In that work, they're interested in estimating the membership matrix. Here, they're interested in estimating Z of this form, and then there's a procedure for computing a Z hat from your matrix U of leading eigenvectors. Okay. All right. So now let's have a quick look at an L infinity perturbation bound for the rank 1 setting. Right. Here we're going to assume that E has Gaussian noise. Suppose IID Gaussian noise on and above the main diagonal. Now we're going to define this quantity mu as equal to n times U star in infinity norm squared. Okay. Mu is what's called an incoherence parameter. And it's just a sort of a convenient way of translating the possible form that, well, the infinity norm takes, or more generally, the 2 to infinity norm, right? So we know that this is true for the 2 to infinity norm. Here, we have just a single vector, so this is the same as the L infinity vector norm, and now we're just scaling by n and taking a square. This is called the incoherence.
I guess it's implicit that the norm if U star is 1, the L2 norm.
That's right. Here, all these eigenvectors are unit norm. That's right. That's right. That's right. Yep. So now, the sort of the informal claim is that if your signal eigenvalue is sufficiently large, and this is something determined by the noise level of E, right? Remember that E is with high probability no larger than order sigma root n. And we have a bound on the distance between these two. This is a uniform bound on how close these vectors are. That looks like sigma times root log n plus square root lambda, mu over lambda star. Right, and so now what we notice that is, well, if mu is no larger than log n, right, then what we have is a sigma root log n over lambda star. Right? And we can compare that to our previous distance and operator norm, or here just, let's say, an L2. Right, and remember that there, with high probability, we have sigma n rho over lambda star. Actually, let me get rid of rho. This is in the L2 norm sense. So here, what this is saying is, well, as we become more and more localized, actually the bound deteriorates. Right? The bound deteriorates up to the point that, well, let's see, if we have a localized vector, right, then this just looks like order square root n, and then we are no better than our benchmark in L2. Right, so there's sort of a spectrum, if you will. And so for this delocalized case, notice we're getting an improvement that is of the order root log n over n, right? Now, we haven't fully achieved, I mean, this 1 over root n factor, but there is some noise and fluctuation in the model, so this log is not a problem or unexpected, per se. So again, in summary, if you have sufficient delocalization, then you can get entry-wise perturbation arguments that are uniform over all elements of your vector here that are better than in the L2 norm sense. Right? And I mean, yes, the L2 norm is itself in some ways uniform, but it's aggregating the error over all elements. Right? Here we're not aggregating, we're looking at worst case by just comparing the entries. All right. Now, the perturbation landscape for entry-wise and row-wise analysis is much more intricate than in the L2 norm sense. Like very loosely speaking, the operator norm, Frobenius norm, perturbation space is relatively smooth and simple, but not so in the entry-wise setting. The properties of U star matter, as we see here. Assumptions on your noise matrix matter. If we allow more general low-rank R structure, then that matters. And so we shouldn't hope for sort of the cleanest or simplest statements of results for perturbation theory. So here, now if we extend our discussion beyond just a single vector to talk about the rank R perturbation setting, I mean, again, what we have is A is A star plus E, right? We have some assumptions such as mean zero noise, bounded elements for simplicity, uniformly bounded variance. Okay, right? So first, at least the first two moments exist, and some other assumptions. Here we have a kappa. This is the condition number at the population level. So thinking about the aspect ratio of your low rank matrix, right here. This is U star, lambda star, U star transpose, right? So we have two bounds here. One is exactly on the 2 to infinity norm of U hat minus U star W. Okay. The other is a bound on U. U minus M U star lambda star negative 1 W, right? Next time, or next lecture, time permitting, I'll elaborate a little bit on what exactly is going on here. The punchline is that there are some situations where, U, the sample eigenvectors, are actually estimating this matrix more sort of in a stronger sense than just the population matrix of leading eigenvectors. There's sort of a slight modification or correction, if you will, for the population eigenvectors, and what we can establish is a uniform bound for that expression. All of the ingredients we've been talking about so far continue to appear here, right? We see denominator terms depending on the population eigenvalues, right? So as our eigenvalue at the population level gets larger, our bound gets better. Right? As the rank grows, the bounds deteriorate. As the noise level measured here through sigma, as this gets larger, the bound deteriorates. As the aspect ratio between the aspect ratio for the population eigenvalues becomes more drastic, the bound deteriorates. Right, but certainly much more complicated than what we saw previously for something like this. All right, so next lecture, which will be the final lecture of this mini course, we're going to revisit this idea, investigate it in a little bit more detail, and I also want to spend some time talking about ideas behind proof techniques, because I think it's illustrative to see how we can start to get bounds of this form. Right. Thanks, everyone.